The path to the moon is defined by a paradox. To reach a place governed by gravity, we must first defy it, and the systems built for that defiance are judged by the very laws they seek to escape. The Starship lunar refueling architecture embodies this technical paradox, designed to simplify lunar transit by removing complexity from the launch pad and relocating it to low Earth orbit, where the consequences of complexity multiply invisibly. The plan for Artemis III depends entirely on this orbital choreography. Multiple tankers dock sequentially, propellant flows across a mechanical bridge to arm the lander for its translunar injection burn, and the entire sequence relies on pure pressure, precise valve timing, and the unforgiving constraint of time. This transfer system, intended to make lunar flight inevitable, sits one assumption away from failure, risking collapse through the very simplicity of its design. The core engineering mechanics are rooted in the massive, thin-walled stainless steel tanks containing liquid methane and liquid oxygen, held at cryogenic temperatures. The transfer is driven by autogenous pressurization, where gasified propellant is routed back into the tanks to maintain the required pressure differential, typically 0.2 to 0.4 bar, to initiate flow. Docking is executed by forward ports with redundant seals and hard capture latches, sized for the high mass flow rates required to complete the transfer within the mission's operational window. The entire orbital rendezvous sequence is managed by a control loop that integrates multiple sensor types, fine-tuned for closure rates measured in centimeters per second. In the vacuum of orbit, the absence of natural gravity transforms fluid behavior, necessitating a dedicated low-acceleration settle burn to align the free propellant surface with the suction pickup. However, the wide tank geometry and internal baffles foster capillary action, which traps small gas pockets. Prior cryogenic test records show that a trapped pocket of just a few liters can break loose during line opening, causing a downstream pressure spike of 0.11–0.2 bar for a fraction of a second. This minor physical event can confuse control loops that model the tanks as simple volumes, leading the software to overcorrect the system state. The non-negotiable arithmetic of the mass budget imposes a continuous fight against entropy. Each tanker must deliver the net mass remaining after inevitable losses due to boil-off and line conditioning, with projected boil-off rates ranging from 0.05% to 0.15% per orbit. A chain of 8 to 12 tankers accumulates losses measured in tons. An unexpected delay or extended Earth shadowing introduces Kelvin-level temperature swings that significantly magnify this loss. If the architecture demands 95% of the nominal mass, but the chain yields only 92%, the missing delta V for translunar injection means the mission Starship cannot depart. The human and institutional decision logic supporting this rests on a trio of assumptions proven brittle by fluid dynamics. The first fallacy is the belief that tank pressure is an instantly tunable knob. In reality, the autogenous pressurization system is tied to engine cycles and heat exchange, introducing lag. The second failing assumption is the reliance on averages for parameters like valve latency and boil-off rate, when the true threat lies in the outliers. The third is the premise that the docking interface becomes a rigid body post-capture. In truth, the joint remains an active mechanical spring, and the connected vehicles form a coupled oscillator excited by every burn and valve actuation. This coupling manifests in a critical systemic risk, the flow reversal event, a quiet collapse of stability. It begins when the donor tank's autogenous loop lags the command by 200 to 300 milliseconds, often due to condensation clearing in a cold valve body. During this lag, the donor tank cannot restore pressure fast enough, and the receiver tank momentarily holds a higher pressure, causing the flow to reverse for a transient period, sometimes lasting 0.6 to 1.2 seconds. If this reversal persists for longer than about 0.5 seconds, the liquid column continuity in the transfer line can be lost. creating multi-hertz oscillation that wears down seals. If the event extends beyond 2.0 seconds, the system risks choked flow discontinuities that force an automatic safing abort, ending the transfer before completion. The margin between a recoverable event and a hard abort can be less than 1.5 seconds. The intellectual payoff lies in dissecting the causal architecture underlying this reversal, which is mathematically located at the intersection of thermal fluid lag and gas compressibility dynamics. The core mechanism involves 4 coupled layers. Thermal fluid lag introduces the 200-300 millisecond delay in gas delivery due to recondensation in a cold spot, causing the control loop to initiate a pressure failure. As the pressure differential shrinks, pressure symmetry collapses, and the line cools faster, increasing fluid restriction. This allows gas compressibility to dominate, causing small disturbances to grow without linear restraint. The third layer initiates vapor ingestion and oscillation. Slosh exposes the pickup to gas, and when the slug enters the line, the speed of sound drops instantly, creating reflected waves. The final layer is structural coupling. The oscillation torque feeds directly into the docking port, forcing the clamps to cycle tiny deflections of 0.2–0.4 millimeters, introducing alternating stress that risks fatigue crack initiation over many cycles. This quantification of the near miss reveals that the difference between a mission continuing after a brief reset and an abort that deletes the translunar injection window is measured not in tons of fuel, but in milliseconds of flow stability. The worst outcome, the damage branch, involves a micro crack forming at the flange root, unseen by sensors, introducing a rising unseen risk to subsequent missions until the joint fails under load. The complexity of the architecture forced an unavoidable trade-off. If the control loop is tuned conservatively to compensate for the 200–300 millisecond lag, it must reduce the propellant throughput rate, which requires more tankers to complete the same transfer mass, complicating the operational schedule. The final logistical decision is a trade study between physics and schedule. This confrontation with physical limits is not unprecedented. The history of the Space Shuttle Columbia disaster, STS-107, serves as a stark antecedent. A system engineered to withstand hours of Mach 18 re-entry plasma collapsed not from a main engine failure, but from a tiny breach that allowed thermal ingress. The cause was the strike of a piece of foam insulation from the external tank that hit the reinforced carbon-carbon (RCC) leading edge of the left wing during ascent, creating a hole approximately 15 by 25 centimeters. Once the breach existed, the high enthalpy plasma of re-entry was directed into the wing's internal aluminum structure, which quickly lost its yield strength. The vehicle's control systems masked the crisis for several minutes by fighting the growing lift-drag asymmetry until the structure failed near the wing root under combined aerodynamic and thermal loads, leading to total breakup. The organizational failure that preceded the physical collapse was the normalization of recurring foam shedding. Because previous missions had survived foam strikes without catastrophic loss, the decision logic established that the risk to the RCC was marginal. This logic was fatally flawed. Survival proved only that a near miss had occurred, not that the damage was benign. The lesson enforced post-accident was procedural and absolute. Treat every anomaly as a precursor, not as noise. The redesigns included establishing formal on-orbit imagery requests and institutionalizing a barrier against raising dissent, requiring managers to treat trend as a warning rather than a reassurance. Returning to the ongoing risk in the Starship Refueling, a set of unresolved variables remains that cannot be fully tested on Earth. The true long-term performance of cryogenic seals when cycled hundreds of times in orbit is an unknown. Similarly, the aggregate fatigue of the docking flanges from many small off-axis loads remains a factor of controlled uncertainty. An operational ceiling must be established for how many tankers can successfully queue and dock without their attitude control thrusters cross-coupling and destabilizing the stack. NASA may impose a minimum threshold of incident-free transfers, such as 25 to 50 cycles, before permitting crewed operations, confirming that repeatability is the true measure of robustness. The policy changes that may follow the test must be structural. They could involve adding small electric pumps to give control authority when the pressure differential collapses, or implementing tighter control deadbands to suppress attitude thruster phase additions. Closure is found in the final, quiet certainty that physics always provides the final verdict. The Moon accepts only the energy delivered by the system, measured in precise delta-V. The Starship Refueling concept is a control problem dominated by thermal fluid delay, requiring predictive control to anticipate lag rather than react to it. The belief that a system without pumps operates without dynamics is an illusion. Pressure-driven flow contains stored energy, and oscillations are an inevitable feature of its operation. In the millisecond window where stability is won or lost, the verdict is private, delivered to a control loop that either anticipated the lag or did not. If the discipline to hear the quiet warning of failure is not applied, the path to the Moon remains, but it recedes, made longer by 1 millisecond of control lag, 1 millimeter of joint deflection, and 1 missing bar of pressure at a time. Success in space is a clean line hiding the jagged edges below, and the greatest risk remains the temptation to declare mastery where only temporary alignment with natural law has been achieved.